Gravity settler is a simply long chamber. Flow is going from one way and go out from the other way. So while the flow is going from one side to the other, the particles settle by gravity in this chamber, in the middle chamber, which has the length L and the width W. The cross-section area is W times H and is much larger than the duct that's approaching it. See this? Just use the pointer. So this is the duct approaching it, so small, and it keeps getting larger until it reaches the chamber where actually the magic happens. So the gas velocity inside the chamber is much less than either of the two ducts because they have smaller. So where Q, just use the pen, try to use the pen again. Q is equal to A times B. So in the inlet here, where you have small a, you have large B, while here, where you have large A, you have small b. So the baffles of some kind are used to spread the incoming flow evenly. So what are baffles? Baffles are vanes or resistance that actually pushes the air in one direction, similar to what you have on your fan or your AC. You know, the things that switches the direction of the flow in one direction to the other. These are called baffles. So baffles of some kind are used to spread the flow, where these baffles are here. And see the inlet baffles to spread the incoming flow so that you can use the entire area. It's not, the flow is not just concentrated in the middle section. V average is equal to Q over WH. So where is this coming from? Again, we said after Q is equal to A times B, so Q is equal to WH times B. Therefore, V is equal to Q over WH. And we also know that V is equal to L over T. So the velocity is usual distance over time. So we can also say that T is equal to L over V, which is also equal to L over, and we can take the V from here. So it will be WH over Q. So the T will be equals to LQ over WH. So the vertical settling distance, TVT, is equal to VT times L over V average. If the vertical settling distance is more than H, which is the original distance above the floor. Then it reach the chamber floor and be captured. If all particles are equal size, which is same Vt, there is a distance above the floor at which the inlet below which all particles are captured and above which of them will be captured. So the vertical settling distance is the distance that's really needed to settle all the particles, which is equal to T times Vt of the particles. It's equal to Vt over L times L over V average. We have two types of flow. We have the block flow and the mixed flow. Looking at the block flow, the fraction captured, eta, is equal to LVT over HV average, which is also equal to LG d squared rho particle over HV average 18 mu, where mu is the viscosity of the fluid. Now, assuming mixing in the vertical direction, fraction collected, which is VT dt over H, and the change in concentration collected, which is dC, that's equal to negative C, equal to CVT dt over H. The time it takes to pass through the section in a small section is dt equals to dx over V average. If we substitute, we become dC over C is equal to negative VT dx over HV average. If we integrate this one, then we'll get len C out over Cn is equal to negative VTL over HV average. So this is your final rule for block flow. For mixed flow, the eta is equal to 1 minus C out over Cn, which is 1 minus e to the negative VTL over HV average, which is again from top, from this one here, equals to 1 minus e to the negative g d square rho particle L over 18 mu HV average, which gets to us that eta mixed is equal to 1 minus e to the power negative eta block. So let's try to solve an example. Look how we can tackle this. Compute the efficiency diameter relation for a gravity settler that has H is equal to 2 meter, L is equal to 10 meter, V average is equal to 1 meter per second for both the block and mixed flow models, assuming Stokes law. So let's start with the block. With the block, we know that we can use this formula over here, the first one for the block. So LG d square rho particle over HV average 18 mu. So we substitute L10 G 9.81 d square 10 to the power negative 6 to the power 2 times 2000, which is the rho, over 18 mu, and the H and E average is 2 and 1. We come up with 3.03 times 10 to the power negative 4. From the very last rule here, we know that eta mixed is equal to 1 minus eta block. So we'll use this formula to get that eta mixed is equal to 1 minus e to the power negative 3.03 times 10 to the power negative 4, which is 3.029 times 10 to the power negative 4. So this is the values, the two values, eta block and eta mixed, for the particle size of 10 to the power negative 5 meters, which is 10 micrometer. If we do this calculations for different particle sizes, everything else will be constant, but then we can calculate it. This is the one for for 10, but we can calculate it for 1, 30, 50, and so on, and we can keep going. So we can come up with this curve here on the right, where we have the x-axis is the particle diameter, d in micrometers, and here we have collection efficiency on the y-axis. We can actually see that the mixed and the block particles, they are the same at really almost the same at very small concentrations. Sorry, that's very small particle diameters, but they start to be that far away from each other when you go into larger diameters, which tells you that these models, they agree somewhere and they disagree somewhere else. Next video will be about centrifugal separations, which are also called the cyclones.